Yo, what's up, everybody? Welcome back. Today we are working on writing a GPU driver, and we are on day 4, I think, of this particular part of the project. And today's topic is trying to get it to actually display something. So we've been working on this example application where we kind of write with a raw Linux graphics calls to like kernel mode setting. We would display this little smiley face and he blinks every once in a while. We just added that this morning. But he's a little exciting. And so what you're seeing right now is in QEMU, we are opening up a handle to a graphics card, which is not the graphics card that we're working with right now. And we are drawing to a frame buffer, basically just like writing pixels like manually on the CPU and then asking the GPU to display those on the monitor that's plugged into it. The goal is for us to be able to do the same thing with our GPU. So we are implementing a second virtual GPU, much shittier than this one, just to try to understand what does a GPU do, right? Because we have this like idea that at some point in the future we'll want to make our own GPU. That would be kind of like a fun thing to do. But in order to do that, it's like, what does like a GPU actually do is something that is like not really clear in my head right now, right? Because you write like OpenGL, and he calls into like some cloud of stuff, but we kind of know that there's like Mesa and like EGL and like Vulkan and like OpenGL, right? There's like just like tons of stuff in here, right? And then we kind of know that like below that there's like the kernel, and we know that he has like DRIKMS. These are like words that we've heard. Gem is another word we've heard. And then like below all of that, PCI, I guess, is like an actual GPU. And so what we were trying to understand by going through this process is what goes on here and what goes on here and what goes on here. So we're kind of at this point right now where we're not really working with like any 3D rendering APIs, but we are implementing a kernel driver for a virtualized GPU that we are writing. And we're trying to see like, okay, what's required to get something to display on the screen, which kind of lets us answer like a question of like, what is all this stuff? And so we are at the point right now where if we run that same test application, so let's kill this version and start it on card 1. This card 1 is our device. So if we look at like, I guess we printing things here, right? So if I look at like here, he says, hey, we are a Sphero GPU. And we ask him for like what monitor is plugged in, what his resolution is, and then we like set up some frame buffers for rendering, and we like dispatch those to our GPU. And we're using all the same code that we're using for the other GPU, so we're using like generic Linux interfaces for this. And in our GPU, we start to see like we are getting data. We've kind of got to the point where from the user space perspective, our driver works. Right? But the problem is that our driver doesn't do anything, right? He just kind of like takes the memory and then just like spits it back on the ground. We need to like actually like send that memory back over to a PCI device that we are implementing and do something with it. So that's the plan for the day, is to kind of figure out how like the DMA transfer to a PCI device will work. Then once we have like sent memory over to the QEMU host, we should try like maybe writing out what we get into like a image on disk or something, just to prove that like we have done the DMA transfer successfully. And then once we've done that, we can try to integrate with like their little GUI interface in the same way that the other GPU was. That is the plan, and I think we can just kind of jump in. We are at 03:55, and it's time to try to copy some pixels to the host memory. Is this a GPU as it applies only to graphics, like no compute pipeline? I don't know. Who knows? I haven't really thought this all the way through at all. So we'll kind of just see what happens. We'll see what happens. I imagine that what we'll find out is that modern GPUs basically are just like compute devices, would be my guess. I don't know if that's true, right? But that would be my guess. And so we might end up getting something like parallel compute for free. Maybe. Depending on what happens. We'll see. We'll see. Okay. So the way our like memory management works right now is, let's see. I guess like driver architecture. So we call somebody, we register as a PCI device with a specific PCI device ID that we have matched on like in QEMU. The PCI bus goes like, oh, I found a PCI device. Hey, I'll call your probe function. We set some stuff up. We say like, hey, DRM system, i.e. direct rendering manager, I think, could we like register our device? And so we like set up a device and we set up like some parameters for him. Things like, hey, we have a connector. We have a connector, and here's how you determine if that connector is detected. And so like one of the things that we'll do is we will like read a register from the PCI device and we'll check that it says cafe food. If it says cafe food, we say that it's yum yum food time. We have a monitor plugged in. He goes, we've kind of like gone through a few days just like kind of like trying stuff, following crashes and getting to the point where we have everything connected. And the important piece that we need to look at now is every time somebody tries to apply configuration, i.e. they say, I want to render at this resolution with this frame buffer to this monitor, essentially, to this connector. That ends up in this function. Let's see if we can find it. Probably in here somewhere. Probably in here somewhere. Here. This plain update function. And so what we have been doing right now is like previously somewhere before in the code, they asked us to allocate a buffer. So I think it's create DOM is what we called it. We kind of create this like gem handle where gem is I think called graphics execution manager. And it's kind of like this like collection of utilities that are useful for GPU driver development that also have some sort of like user space API associated with them. So in this case, what we were doing is we're creating like a shared memory handle or a shared memory section of RAM, and then attaching that with like an ID for like gem handles. So like you can imagine like texture ID kind of is like a similar concept here. And when we create this thing, we get a handle, we send that back to user space. User space comes back and they say, hey, I want to render that thing. So they attach that to a frame buffer, which basically has like width, height, pitch, pixel format stuff gets like tied to the buffer. And so then that comes in to our function here as a plane. So it goes like buffer, frame buffer, plane, monitor stuff, kind of. And so buffer is like raw data, frame buffer is like width, height, pixel format, and plane is like, what did we read this morning? It's kind of like if your frame buffer is like 1080p, but your monitor is like 240p, then plane kind of like holds that mapping. He goes like, okay, how do I connect this frame buffer to this monitor? Do we like scale it? Do we truncate it? Like how does this shit fit? And then you can also have like multiple planes. But anyways, so that's what we're seeing here is he's coming in with like a request for a new state. And so we look at the frame buffer and we say, okay, we know that we attached one object to this thing earlier. And that's this. And so we can pull back our shared memory thing out. And we call this get scatter gather table thing, right? So when we allocate this memory, we treat it in our process like it's like a contiguous chunk of memory, but that's not true, right? In reality, pages are kind of allocated in 4 kilobyte chunks and kind of spread out across the system. And so this is like kind of the way to say, hey, I know that I'm going to want to transfer this thing to a piece of hardware that doesn't know our virtual mappings. And maybe it could, but we want this transfer to be able to continue happening while we switch processes and do other things, right? So really we want like physical pages. And technically there's a difference here between physical pages and DMA pages, where DMA stands for direct memory access. The PCI bus is directly accessing memory. But I think like for all purposes for today, we can consider those the same. I suspect that there's something like you could maybe possibly have DMA-able addresses that are not accessible to your physical memory in some way. I'm not entirely sure. Maybe there's extra restrictions, not sure there. But we can basically iterate each page, I shouldn't say each page, each contiguous chunk of physical memory. We iterate these things and we can like do some stuff with them. So previously we were just mapping them back to virtual memory and logging things about them, such as like how many yellow pixels we saw, how many black pixels we saw. But here is where we should do the actual work. And so it should be something along the lines of sgdma address here. So we say u64 DMA adder is equal to this. We are going to need to take out the length. So sg length, I think it's, well, let's look at what they do in our reference driver, vert IO GPU. This is what we've been kind of like just copying what they do. And they call, I think they did it kind of earlier in the pipeline than we're doing it. So can we maybe figure out where they did that? Here. They call DMA address, then they make sure it's Little Indian, and then they just put here, oh, it's SGDMA len. That's what we're looking for. SGDMA len. I guess I kind of want to keep this thing open here for reference. Sphero derv. That's where everything's going. And I guess it kind of makes sense for them to do it this way. So this function is called like on every page flip. I guess technically you should really only upload one time and then just like reference later. But for now, we will just upload all of everything every time because we're lazy pieces of shit. And we're not really too worried about performance right now. We're more worried about seeing something happen. Okay, so we have like a DMA address, DMA len. So here we should probably do the same thing they're doing, CPU to LE64. I think that's like pretty fair. Even though we're only ever going to be running this on a Little Indian machine, we might as well. We might as well. So here we'll take the length. And we are going to have to do something with this, right? So my idea right now is just that we like write to the PCI device at like a specific memory location that says, here's where you can pull memory from. So I kind of want to do something like DMA adder. So our register interface is kind of 32 bits right now. So we will have to account for that. We also need like access to our device here. So I think we can get like a Sphero priv is from DRM dev private data here. And then we can just do like priv regs 1. I think we have used 0 is connector ID. And so we can use 1 and 2 are going to be like DMA address. 3 and 4 will be DMA length. Okay. And I think that we're just going to do is like, we're just going to write to these things. And on the other side, every time we notice somebody writes these, we will start using that information. And we just have to figure out, we have to say like, which one of these 4 register writes will trigger the actual transfer. And we'll just say number 4. We'll just say number 4. So 1 is going to be DMA adder. I have to be careful here. So if we're doing Little Indian, I guess this should be the lower bit. So it's just like this. Oops, not equals equals. 2 will be this shifted right by 32. And then I guess fix me with above LE64. This could be wrong. Right? Really, it's probably we should do a CPU to LE32. Right? Kind of like this. I think that makes more sense, yeah. I think that makes more sense. Because you kind of have to do like maybe like inner byte order swapping if it was big Indian here. So we'll kind of do this way. No problem with that. And then 3 is going to be the DMA length. And 4 is DMA length shift left by 32. Boom. Simple. Simple, simple, simple. And now theoretically, that's everything we need. Now, I think we might need to do some sort of like syncing for GPU access. It feels like that's something that we might need to do. DMA fence wait. So where the fuck are we? Here. So this function, they get the scattered gather table. They prepare the transfer, but they don't actually do the transfer yet here. They do the transfer kind of down here. So I don't know if I see any fencing here. GPU fence. Now that the position of VBuff and the vert queue is known, we can finally set the fence ID. Yeah, I think it's probably fine. It's probably fine. We'll see what happens. It might not be fine, but it might be fine enough for now. Okay, sure. So then we can get rid of some of this like other tracking stuff. We don't really need to do these counts anymore. We kind of understand what's happening. And this print K can go away. All right. So as long as the data is like consistent, as long as like this stuff doesn't get like reordered, which it might, I think that it should be sane to say that this is the last thing will happen. I don't know if we're supposed to like do this to say that like orders, like order of operations can't change. Is that what volatile does? I can never remember what this does. I just know that it's never what I thought it would do. In C and C++, type qualifier like const is part of the type. Behavior of volatile keyword in C and C++ is sometimes given in terms of suppressing optimizations of an optimizing compiler. 1. Don't remove existing volatile read and writes. 2. Don't add new volatile reads and writes. And 3. Don't reorder volatile reads and writes. However, this definition is only an approximation of the benefit for new learners, and the approximate definition should not be relied upon to write real-world code. Allow access to memory mapped IO devices, which is what we have. Allow preserving values across a long jump. Allow sharing values between signal handlers and less program. The C++ standards allow writing portable code. Blah, blah, blah. Any other use of volatile keyword is inherently non-portable or incorrect. In particular, writing code with volatile keyword for memory mapped IO devices is inherently non-portable and always requires deep knowledge. Okay, I don't have deep knowledge, so we'll just kind of keep it like this and just see what happens. Because I think that the mmap basically don't cache, always assume read and write. But it's kind of saying that's not what it is. That's kind of like my understanding, but then like this says it's basically not that. In particular, writing code with the volatile keyword for memory mapped IO devices is inherently non-portable. Can we look at like what someone else does when they do this like PCI bar mapping? Like IO adder here. He just tags it with IO mem. No deref address space. Yeah, it does just look like they tag it with IO mem, which does nothing in our case. But we can do this anyways, just for funsies. Hello, is this about kernel? Yes, I guess. I don't really. Why did he say it isn't saying that? I'm basically saying that because he's saying that this is always non-portable and requires deep knowledge. So I was just like, that makes me think like, I don't know, I don't know. I will follow behavior of other people though, because I assume also that this IO remap thing under the hood is performing operations so that it will work correctly. I think, but maybe I'm wrong. Maybe I'm wrong. I don't know. We'll see what happens. Ultimate means that the underlying address is volatile, like memory map things. All right. Fuck it. Let's just run it and see what happens. Okay, so I guess what we want to do now is we want to go into our QEMU driver. So let's get in there. Let's get in there and update our device. Didn't we delete a bunch of this stuff before? This doesn't look right. Oh, this isn't source backup. That's why. Source QEMU. There we go. There we go. Okay, so we said we have 1, 2, 3, and 4. And we said that this should set the lower 8 bits of the lower 32 bits of the address is what we said here. So here we'll say that we have like an address. DMA address is going to be a U64. So here we'll say DMA, we have our state. DMA address is, I guess we need to like clear the bottom 32 bits. And then we need to clear the bottom 32 bits first. So, and there's FF 00000000, right? And then we OR back in data in this, right? Right? I guess we could even do, that's fine. It's good enough. Good enough. Okay. I don't know why this indenting is doing what it's doing, but I don't like it. I don't like it at all. So I'm going to do what I want, and then maybe he'll get mad at me. So this one is the other way around, is we want to clear the top bits. And then we want to shift this right by 30, left by 32. Okay, and then this is going to be the same here for the DMA len. Okay. So I guess it's just the same shit. The same shit for this. But the inputs are going to be like this. And then when we write the final register, here we actually have to do some work. So here we're going to do, right, like call like do DMA with S, I guess. And I guess we should call it Sphero do DMA because in this language, there's no namespacing, so you have to fucking prefix everything with your thing. So this is going to be a Sphero state pointer as our input. And I guess we just need to look for an example of this in the QEMU code. So presumably in like vert IO GPU stuff, they must at some point map some memory. Phys hostmem image create bits. Okay, wait, what is this? Ret hostmem. This is a uint64. I guess maybe we should look maybe a little closer at like vert IO. We had it open somewhere. Transfer to host 2D sounds promising. So when they do a, no, I don't want cursor plane update. I want the primary plane update. So when they do a primary plane update, they set the scanout blob. And then they do a Q control buffer. Okay. Geez. Add SGS, vert Q add, scatter gather, something. Oh, it's not easy. I think I saw it in the vert IO GPU code before. It was like Pixman something. They like figure out. They like construct this image from the data that they got that they pulled in. I'm pretty sure. This. Yeah. This is what I'm looking for. Pixman image create bits based off buffer, the M-mapped buffer here. So where does this get set? UDMA map buffer object. I'm willing to look like okay, res buffer. So this comes from VG resource create 2D given their command. So their command has a resource ID and they create a buffer. But where do they actually map the stuff in? Res buffer comes from this. So is this an output? Yeah, this is an output. Okay. Okay. So then this stuff comes from the mmap buffer here. So that must mean that in here they have an mmap. Here. Which they call map buffer object on. I see. So this is dev map bo, where dev is a vug boom device, which comes in here as their second parameter here. So in here they have map bo. Sure. So they have like, if we have GBM, otherwise this, other than that. So QEMU host, real, this seems real host page size. That's not what I want. Somewhere they must be getting the memory from the fucking virtual machine, and I'm missing that somewhere. We're missing that somewhere. And I'm pretty sure I understood this at some point. Vert.io simple resource. Format iovec image buffer. Yeah, I mean, it really does feel like this is like an M-mapped host thing. So maybe they M-map some guest memory into the host somehow. That seems possible. So where do they set this again? I think we're in this path or this path. So say we were in the UDMA path. They just mmap from buff mmfd. Okay. Which just comes from an allocation here. So they're allocating on the host side. So they allocate on the host side, but then how do they transfer the data then? Sure. So they maybe they have to copy the memory out in their version. That seems possible. That seems possible, in which case we should be looking for like whatever the command was, like some sort of like resource 2D upload. Vert GPU derv. Oops, wrong thing. I'm looking in here. Vert gyro GPU. Okay, so where do they like handle control? Process command queue. Process command. create resource 2D. Was this what we're looking for? Create bits. So this is like host memory allocation. Then when they transfer to host 2D, this is probably where it actually comes in. They like get their resource and then they must copy the stuff out. IOVec to buffer. Here we go. So I assume that this like takes the values of the stuff in this thing and kind of chunk by chunk takes the things in here and puts them into image data, which kind of lines up with the idea of like a DMA transfer being like fragmented, in which case now it's like, how does this IOV get set? Right, like vert IO GPU load. This is a kind of general thing. I'm somewhere somewhere in here. We should look for where they actually assigned those pages. I think that's probably the key here. So that was in vert IO GPU display. Vert GPU, wrong fucking window. Vert GPU paid plane. And we saw ents. No. Sphero derv. We were looking for SG DMA address in vert IO stuff. Vert GPU display maybe? Oh my god. Fuck. It's in one of these. Vert GPU here. Here it is. Okay. So the question is where does this transfer go? That's the key. That's the key to this, right? So here he's going to call vert GPU object attach with the entities. And it's resource attach backing. That's the call we're looking for. Resource attach backing. GPU create mapping IOV. This looks like what we're looking for. So DMA memory map. Map a physical memory region to a host virtual address. Nice. May map a subset of the requested range. Right, so he kind of takes each of these chunks and maps them individually. We can kind of just say, fuck it. We'll map this temporarily and copy it out or something. Let's think about this. So how can we simplify this? Also, is there like a free for this DMA memory map? Surely there's like an equivalent DMA memory map. Okay, cool. So this is really the only thing that we care about right now. So Sphero GPU, Sphero derv, Sphero.c. Yeah, there we go, found it. Boom. All right, so now we have to figure out just what the fuck all of these parameters are. Address space. So this must get just assigned somewhere. This is, does this have like, describes an address mapping to memory region objects. Okay. So what's vdev here? Vert IO device. So can we look at like realize their initialize function? This creates a vert IO device. Nice. So we're looking for here somewhere that looks like they're setting up the address space thing. which might come from, this just calls like the base class realize. Device plugged. Oh, here? VDev DMA AS. Okay, so they set up a listener for that thing, but how do they like initialize that guy? VDev is the vert IO device, right? Okay. Bus plugged. Jeez, man. Oh, here we go. If we have get DMA AS, then we assign it that way. So how do they do this? For a PCI thing, they do this, which just says PCI get address space. Okay. I mean, that seems reasonable to me, right? We our PCI device, we need to have an address space associated with that thing, I guess. Sure. Who fucking knows, man? We'll run it and we'll see. So PCI get fuck. What was it? PCI get address space. So here we must have to do this somewhere. So we have like address space here. And then we do this on realize. And then we say SAS equal this, I guess. I guess. First argument down. First argument down. DMA memory map. Okay, what is his second argument? Res adders. So this is just an output argument. Address within that address space. Oh, the input argument. Len, direction, and attributes. Okay. Oh, that should be pretty easy. That should be pretty easy. Should be. So the address is S DMA address. And the len is S DMA len. And now we just are missing like, there's probably like a void star. I don't know. Undefined, unused variable map. Okay. Then he doesn't like pointer conversion, so we just kind of fucking. That's definitely the same thing. This is unit 64, so I don't know why he's mad about this. Len is a pointer? Oh, updated on return. So he wants us to be kind of like this. I guess because maybe this is going to like, the output length might not be the same as the input length for whatever reason, I guess. But I think we're chilling then. I think we're chilling. So now, we probably want to do the same test we did on the driver and like count how many of each color we get. I think that makes a lot of sense. And I guess somewhere we need to indicate a new frame as well. So maybe we'll have a 5 that like, right, because we have like the concept of like a page, but many pages are related to one frame. So maybe we want to do like Sphero reset frame S here. Yeah. Sphero reset frame. Okay. And here we will basically just zero out some parameters. So we can do something like count num yellow pixels, num black, num other, and then on reset frame we will print those things. Seems reasonable. So here we're just gonna like call this a uint32t pointer iterator. We're gonna go for 0 to len over 4. Map I. This is not how you do for loops in this language. Unit 64t I equals 0. I is less than len over 4 plus I. Map I. And we're going to say if this is yellow, we say s num yellow plus equals 1. Okay. Then else if map I is equal to 0, num black. Else we have num other. We should have no non-yellow or black pixels. That would be a bug. And then we unmap the memory. And he expects a lot of stuff. So address space buffer len. Dir. And whatever the fuck this says. Right? Oh, access len. Wait, so access len, amount of data actually transferred. Len is the buffer length as returned by address space map. So I guess we just type len again. Probably. Right? Because we're touching every single block here. I guess. I don't know. I don't know. And then here we'll say printf yellow, black, other. All right. And let's kind of see what we got. Yellow, S, yellow, S, black, S, other. And hopefully this all just kind of works. I think DMA len for the second arc. I think no, because this len could only be... Okay, so the pointer to like updated round return. So when could this not be the same? Is a question that is not clear to me. Right? It's very unclear. But I feel like if we have actually transferred data out of this thing, then like surely, like if we're using len as our length, we'll also mark the memory as dirty. Access len gives the amount of memory that is actually read or written by the caller to mark as dirty. I think it's however much we looked at, which would be like this stuff, which is just the same. I'm pretty sure. Pretty sure. But I could be wrong. I've been wrong a lot of times in my life, but we might as well just live with it. Build QEMU. Okay, does this build? Ninja x86 64. No, QEMU system x86 64. Let's see what that does. We're chilling, it looks like. Looks like that built. And now we have to set our driver to reset the frame by writing to register 5. Right, so we just write to it, and then that should trigger a print. Yeah, and I guess we have to reset. We only print, we have to reset as well. So here we then do s num yellow equals 0. Everything gets zeroed out. What the fuck is happening? Black and other. And then presumably this stuff has to get set on realize as well when we initialize, I think. Yeah, I don't know. Let's see it. Let's see it. Might as well just fucking give it a shot. Why not? Why not? All right, root test app dev DRI card 1 for our GPU. We didn't compile the kernel, huh? We did not compile the kernel. Let's try it again. Try it again. So test app dev DRI card 1, please. Okay, so we're seeing no prints here from our QEMU, which is a little concerning. A little concerning. So can we check if these writes are going through? Printf writing address, writing len. We could call this writing address 2. Like this, writing len 2. And then reset. We had success with this form of like writing these things when we made our LED thing. That seemed to work. Oops. So I don't really understand why it wouldn't work now. Let's just make sure that this is running the right thing. Build QEMU x86-64. Build QEMU system x86-64. This was built 2146, which is 7 hours in the future, which makes sense because this is PDT and that is probably in UTC for some fucking reason. Okay. Root test app dev DRI card 1. Okay, so he's getting a lot of writes. A lot of writing len 2? And only writing len 2? Which is pretty confusing. I'm down to huck this volatile in there and see what that does. And then we might have to take a look at the disassembly if that doesn't fix it. Just, you know, see what happens. Test app. Yeah, okay, so I don't really understand what's happening here. Because he should definitely be seeing more than that right, I feel like. Hand wavy. Hand wavy, if this is working. But you never know, you never know. So can we... Also, let's look at the API here. It could be that he's kind of writing all of this at once, which would be kind of interesting. We are breaking on all these, right? Break. Switch on adder. So we are just getting adder 4 over and over again. Oh, I'm an idiot, I think. Ignore me real quick. Just, we need to multiply by 4, and I wasn't paying attention. Just ignore me real quick, because there are 4 bytes per U32. Oops. Oopsies. Root test app dev DRI card 1. Much better. In some ways. It looks to me like we are seeing no yellow pixels and everything is black. That does not look good. That does not look phenomenal, I will say. So, I wonder why. It could be that we need to do some sort of like DMA flush from the CPU side. Can we at least maybe, it would be nice to confirm that we are at least trying to read the right values, right? So maybe what we'll do is we'll delete these prints now. And can we just say, like, when we do our DMA, can we How do you do this? Printf. Mapping this for this many bytes. Copying this much from this many bytes. And then we'll look at s DMA address and s DMA len. Okay. We'll start there. This feels backwards. Right? Surely we're going from device. So let's fix that. And then on the driver, printf sending this for this many bytes. Print k here. DMA adder and DMA length. Boom. Format specifies int, LLX, LD, LLU. There you go. There we go. So LX and LU. All right. Ninja. He's mad because he actually wants LU here, I guess. He wants LX, I guess. I don't know why it's different here than in print K, but I'm not going to think about it. Should GPU inform the guest about the finished transfer? Yep, but he's not. That's a problem for another time. We're willing to take some shortcuts around here. We are willing to take some shortcuts for sure. Dev DRI card 1. Okay, so we are sending. These numbers match, which is good. Right, that's pretty damn good for us. Do they match perfectly? So we see like 41E, 65536, 326, and then we see some of these. Then we see some 16384s, 8192s, some 4096s. I think these are right. Like 3 CF000. I kind of lost track. So at the boundary of 496 to 8192s, we're seeing 3CFA 4181. 3CFA 4181. Yeah, so I think we're getting like the right addresses. So it's more likely to be a problem with the transfer. So I'm seeing some pretty quick back-to-back resets, which feels surprising. And I guess maybe we shouldn't be like, how does this work in terms of like when I write these registers and it like does the DMA access here? Like, does this block the write? Like, how does memory work? Like, I have to wait. If I write to memory, I have to wait for it to happen, I assume, right? How does that work? How do we act that? I don't know. I don't know. Okay. Part of me feels like this should be queued up in some way. But I don't really have like a good rationale for that. This feels very strange to me. Oh no, because these are just really, I forgot. Like sometimes we just get like really good contiguous chunks of memory. So the total amount transferred here is probably the same. Although this feels weird to me. This is very few pixels total. Have we fucked that log up? seems like we shouldn't have. Right? This is just going... I mean, something about this doesn't feel right, right? Like, we have, this many bytes, but only this many pixels? Like, that doesn't sound right at all, right? If we have 297,152 plus 827,392 plus 221184 divided by 4, we should be seeing that many numbers, and we're seeing like 3,000. Right? So like 3,000 is way lower than what 780,000, right? Like, that's the right number. So it seems likely that this like memory map is not working correctly. Like the output length is not matching what we expect it to, right? When we were like, what if this, like, how the fuck does this work? Like if we did, may map a subset of the requested range given by and returned to in plen. May return null. If resources need to perform the mapping are exhausted. May map a subset of the requested range. So I guess maybe we need to kind of do like var adder, unit64t adder is equal s DMA address, while adder is less than DMA address plus DMA len. We do this. Right, and so we map from adder here. And then the length here is DMA len minus adder minus s DMA address. Okay. Okay. Then here, hopefully that means that we'll see this, and then we'll do like if len equals 0, break, and printf mapped 0 bytes sag. And let's see if that behaves any differently. Black and yellow, black and yellow, black and yellow. Bump, 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 bump. Are you using the NeoVim LSB client? Yep. So it looks like our question about whether or not things get blocked on the PCI write, that's answered. Now, this is just doing jack shit, which is probably bad. Oh, because I'm actually not increasing address ever. I just forgot. We just forgot, but we should do that. But at least we answered a question that we had. So it's kind of a good thing that we were fuck ups, you know? Oopsie, it's not what I'm trying to do. I'm trying to do this one. Root. Test app. Dev. DRI card 1, please. Okay. So can we look at like what we get in a reset now? Not good. However, maybe consistent? Maybe. I wonder what happens if we just try writing this shit out. Maybe it's worthwhile to just look at the picture. But you never know. You never know. Maybe it's absolutely fucked, but maybe it's like, maybe we can derive something out of this. I'd be interested. I'll be interested to see what it looks like. So, because now at least we're like copying the right amount of stuff. So let's image, I guess. Image data. Pixels. Sure. And then I guess we'll say size t pixels len. And then we will realloc this as we need to. That's not true. We won't do that. We're just going to say that if there's more than 1024 by 768, we'll give up. Just for now. And then what? Boom, 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 boom. What am I trying to do? I guess we want like a pixel index. And on reset, we set this to 0, right? And for good measure, we're gonna say like define pixels len is 1024 by 768, right? So then we can do like memset pixels. Memset always does U8s, right? So it's like 0 and then pixels len times 4 for 4 bytes per pixel, right? Why the fuck does memset take an int? Why the fuck? I should look that up sometime. But whatever. Malloc pixels len times 4. And then do I need to manually cast here, or does it figure it out itself? I can't remember. You can tell I don't write that much C because I have to ask. All right. So I guess on reset, let's write the image out. So I don't know if like QEMU has anything for this, so I'm just gonna like do what I want to do. It's stb image right, I think. Which should just let us take in a bunch of fucking pixelies. And what am I? Hardware Sphero? Hardware Mizik Sphero? Hardware Mizik. What the fuck? Oh, in build, that's why. That's why. Misk Sphero. Oh, and it's just Sphero.c here, so I guess we just curl this thing here now. Because we're being lazy, and how do we write an image here? This. Uh, 1024, 768. What's comp here? Does it tell me compression level? Oh, yeah, sure. Can I just pick, is there like an automatic? Is there like a, no macro here for like define default, you can figure it with the global variables. Default's 8, higher for more compression. Okay. So can I just write like 0 here? I don't fucking know, man. These, there are also 5 equivalent functions that use an arbitrary rate function, blah, blah, blah. Each function returns 0 on failure. The functions create an image. Rectangles W pixels, H tall. Data pointer puts this. Pin creates outputs. Rectangles. Allows you to set the deflate compression level by setting it to the global variable this. Oh, components. I'm just a fucking idiot. Thank you. Thank you. Wasn't paying attention. We would have got there eventually. But maybe like really eventually. I guess technically pitch might not be 1024. It might not be. I guess what we should do. Yeah, there's something on here. And then that's supposed to be in bytes, right? So, but I'm pretty sure it is right now. So I think we're fine. Let's just run it. Let's just run it. He doesn't like this because we need to define STBI image write implementation. And then he's mad because what is he actually pissed off about? Really? No previous type prototype for. Oh, because warnings are treated as errors. Can we do like pragma diagnostic GCC ignored, and then like what's the actual error here? Missing prototypes. Like who fucking gives a shit? Pragma GCC. Is it not Pragma Diagnostics? Pragma GCC Diagnostic? Ignored? Yeah. There we go. It's a fucking annoying way for this to behave, but I guess I get what I get. Okay. Run, baby. Run, 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 run. Okay. Test app dev dri card 1. All right. What happens here? Do we get dolphin here? Yeah, nice. So what does our test PNG look like? I think he's not happy. Oh my god. Oh my god. Dolphin. This is the wrong thing. Test.png. It is just white, huh? I wonder if it's like all alpha. The alpha here might be causing problems. Can we like, yeah, so it's all just kind of like fully transparent. Kind of surprising. It's not what I was expecting. Not what I was expecting. Okay, so reset. Yeah, we are just getting consistent. Okay, let's get rid of these fucking copying logs. It's fucking annoying. And I guess we did see that they called 2device in their version here, which is kind of surprising. Kind of surprising. So we could try going back to 2device. Okay, and then I guess we just run again. And try to look at the logs now. I'm trying to see if like somewhere these start to look sane. You know? You know? root test app dev dri card 1. Yeah, so we were just getting full black when we go from device consistently. And at least when we were going, or to device, and we were going from device, at least it was doing something sane. I don't really believe that I wouldn't be shocked if we have to do some sort of synchronization before doing a DMA. I also wouldn't be surprised if we're just doing the wrong fucking thing on the QEMU side. Both of those seem very likely. So I'd like to see, like, who is another user of this thing? Map PCI into host virtual. I guess I don't think that this is supposed to be PCI address space, huh? Something about that seems kind of suspect, that we got this from the PCI device. Like a little suspect? So like, this is where this was defined though. Which really feels like it comes from this. But I don't really feel like we are mapping from PCI address space. I feel like we're just mapping from like guest physical address space. What's this? Address space memory? Physmem? If VDEV has IMMU, I'd be curious to try just running with this. Just to see if that kind of changes anything. Just to see. Because that does feel a little bit more sane to me. Oh, wait. Here we go. That's looking good. How do I mean, we're seeing yellow and black and 0 other. So now I feel like the PNG we are writing with STB image is not working correctly. It's probably like reverse byte order or something. Probably. So can we look at like data? Can we like look at the pixel format? Four is RGBA. The rectangle is W wide and 4 tall for PNG, stride, and bytes. Oh, wait. Our alpha is assumed to be... We are writing alpha 0. We are writing alpha 0. Which means that here, when we write... can we fix that somehow? Right, like this is just like fucking stupid, right? Oh, we're also just not writing to, we're just not copying into the thing as well. So there's like many stupid things happening here. Many stupid things happening here. Okay, hold on. So our pixel format is supposed to ignore the alpha channel. It's supposed to ignore the alpha channel. And then also we have to actually use the memory. So we have to do pixels plus pixel IDX. We want a mem set or mem copy. This, which way does mem copy go? Source dest or dest source? Dest source, so this comes from map. And we are copying len bytes, right? And then here we're saying pixel idx plus equals len over 4. Wow. Wow. Okay, and then now we have to do the work here of going like for int I equals 0, I is less than s pixel idx I plus plus, and we do s pixels at I or equals RGBA, so it's probably this way, ff00000, because it's little endian, would be my guess. Let's see what happens. Let's see what happens. Run. Run, run, run. Root, test app, dev dri card 1. Oh. Oh, baby. You see that little blinky? Oh, yeah. Oh, yeah. So he's blue instead of yellow. Probably, I wonder why that is. That's not good, because we are seeing this. Oh, because the fucking byte order is swapped, probably. Yeah. So we have to swap. We have to swap. We have to do like. Can you swap? How do you swap to sub bytes here? I guess you just like do temp. Fine. And then we do s. We do like G. Is this RGB? So no, this is B R. BR is this shifted left by 16. Both these have to be like and FF. Okay. Like this. Then we do S pixels I. This is stupid. This is stupid. We should just treat this as uint 8s, and that makes this easier. Pixel is equal to S pixels I. Pixel plus uint 8t temp is equal to pixel plus 1 RGBA. So pixel temp is equal to pixel 2, or sorry, pixel 0. Pixel 2 is equal to temp, and pixel 3 is equal to 0 FF. And then we cast. Okay. Dun 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 bum 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 bum. Okay, let's try again. Root, test app, dev dri card 1. All right, we spam refresh. That's a fucking smiley face blinking if I've ever seen one. All right. So I think we're there. We're kind of like, this is done. And now if we want to integrate with the QEMU display, we have to do a bunch of work. So I think probably we should just try to like add everything. Source Linux, get add -u, get status, Add drivers, GPU, DRM Sphero, get status, commit -m up. Semi-working GPU driver. All right. Do the same with the QEMU. Power Music Sphero, Power Music STP, get commit -m semi-working image right. All right. And then get status in the main directory. Working animation and stuff. Okay. Okay. Let's try to integrate with the QEMU display. So, I have no idea what that means, by the way. Absolutely no idea. But we can figure it out. So I was seeing in the vert.io GPU something like QEMU console create. There's sort of like graphical console something create. Somewhere in here, you can like create one of these guys. And he should give you like a little area that you can just like put shit in, I think. Let's see if I can find anything that matches what I'm remembering. No, okay. We'll just look in vert.io GPU. So somewhere in here, there's like a COM thing. Let's think. So when they write something out, they must, when they get a new frame, they must do something with it, right? They must be like, okay, time to draw that now. Set scan out. Here we go. This looks promising. So DPY replace surface. This looks important. So when we do our frame here, we have this. And then that means that this console thing was important as well. So this comes from here. Graphics console init. And I think we just kind of start like running this shit and seeing like how it looks. Question. If the goal is to understand the software side of the graphics card integration, will there be a step where you'll make your own GPU driver able to work with OpenGL, even a crappy slow one, so the final FPGA card can probably work with 3D acceleration? That's part of like the things I want to investigate for sure. I want to look at I think it's likely that I'm going to make like a software GPU implementation as part of this project and try to implement an OpenGL driver for that thing. So it won't actually do hardware acceleration, but it will seem like it's doing hardware acceleration to the virtual machine. And then I think we'll have a pretty good idea of like what we would have to implement. Because I don't really know if like on the GPU we're supposed to do like, I don't really know like what the boundary is between like shaders and the GPU hardware, right? I would kind of imagine that it's just kind of like you have inputs and you run them through this program. So for each program, the program gets like it run once per input, and that's probably like a generic enough thing that you can implement both vertex and fragment shaders with it, but I don't really know. So I want to at least do the software side of it. But I was wanting to look at, even if we don't end up implementing OpenGL for like this like imaginary GPU that we might make in the future on an FPGA, implementing OpenGL for something should give us an idea of what modern GPUs like how they expect to be used, which is really what I think is the most important thing. Okay. So on our realize function, we have to get a graphic console. So I don't really know what this does. So he takes in a device, so device of us, and a head, 0, I guess. And we have hardware operations, which we will have to implement. And G, what is G here? Opaque. Probably our callback pointer. So we'll put S here. And then we just need our GPU ops. So what do they implement here? Okay, get flags, invalidate display, update display. So all of this stuff is kind of done. UI info, he has some stuff. GPU GLBlock. How much of this stuff do we actually need to implement? Like, is the usage of this stuff all guarded? Boom, boom. So not entirely. Get flags is not. What about like UI info? This is guarded. Oh, that was in vert.io stuff though. Which kind of makes it sound like that there's going to be a... We might need to implement a VGA as well. Unless that's what we were just looking at. GPU ops, which is not the same as VGA ops. Huh. Although vert.io VGA base ops is the same type here, which is kind of interesting. So maybe this thing, graphics console set hardware ops on VGA con. Which, yeah, fuck it. I mean, that might just be like kind of like a bridge thing that we don't need. Kind of feels like it. So I think we just run this here with our Sphero GPU ops, and we just kind of see how this ends up feeling. So this needs QEMU UI or UI console.h. And let's just kind of, I guess we just start by making this and see what happens. Like, how bad can it be? Graphic hardware ops. Sphero GPU ops. And we just kind of put a 0 in here. And something will crash, and then we'll move on. So we need to be in the build directory. We need to run Ninja to run our thing. Sphero GPU ops, I guess. Okay, everyone's happy, maybe. Linking is taking a long time now. I think STB image is really hurting it. Do we have like a Sphero GPU in here? Oh, we do. Okay, I guess it's not initialized display yet, but I mean, that's pretty good. That's pretty good. We have a thing here that we can look at now. So, surely we must initialize this thing somehow. I guess at this point we don't need a STB image anymore, so we can just delete that to like kind of reduce link times. Okay. And what now? What now? I guess somebody must call like somebody must do stuff with this, you know? Vert.io GPU. So like DPI, right? Like surface replace. I mean, someone must initialize this thing somehow. Can we like create a Pixman surface? What's res image here? It's a Pixman image. We probably don't care about that. I guess this thing needs... Okay, what if we just create a placeholder surface? Let's just try that and see if we can see any type of behavior. So, where was that? That was in QEMU. Create placeholder surface. right? So like 10, 24, 768. I'm like, hi, I'm Mick. I want stuff, picture, please. You know, just kind of see what happens. Let's just see. Boom. Boom. Guest does not initialize display yet. So we don't see anything that's like, I want picture, please. Right? So I wonder how, maybe we look at like guest has not initialized the display yet. We look for that and see if we can find wrong window. So this, they do call this, oh, and then they call DPY GFX replace surface, which we saw in the other place as well. So display surface, yes. And this needs the console as its first parameter. So QEMU console C. Right, so I guess maybe we should see something there. Maybe. We'll take a little look-skis. Hi, I'm Mick. I want picture, please. Yeah, that's pretty good. Pretty good. I think we get it now to some extent. So let's add the console here and the surface here. Okay. Now, we probably don't want a placeholder surface, right? We probably want something that's like from an image. I want, like, is Pixman really our only option here? It could be. But we could do it this way, which might be nicer. Might be nicer, because then we only just have to get the right format code. Which it looks like we'll be able to find in here. It looks like we got it fucking the whole world. Probably this one, right? It's either this one or this one. So we'll do this. Display, create display surface from. Create display surface from. QEMU, create display surface from 1024, 768. With the format code next. Yep, and then the line size, 1024 times 4, hopefully. And then the data, which is going to be S pixels. Void star. Cool. Cool. And then we just kind of go, we go like S console here, S display surface here. And if we're lucky, we don't actually have to do anything here. If we're lucky, we can kind of get away with just ripping a reset here. Now, more likely, this is going to be a fucking problem, right? Because we immediately memset that thing. So I was not going to do this at first. And we'll kind of just like overwrite as we go, just to kind of see if that works. That would be cool if it did. Would be cool. Would be cool. Guest does not initialize display yet, but if we go into here and we start writing to it, we crash. Sick. So old surface is not equal to new surface. So we do need to swap the back, the buffer there. Because he's saying, I want these to be different. Right, so we probably need like to double buffer the display surface. Probably. So we'll do this. I forget where the fucking brackets go in this language. And then can we do like this? Pixels 2, 0, and 1 or something. Really? I can't just do... Can I not do it like this? I thought you could. Maybe I'm stupid. Maybe... That's fine. We'll just do it like this. Oh, I want 2 pointers to display surfaces. Okay. And I guess we'll double buffer our pixels too. So pixels, when we create that thing, we malloc twice. Okay, and pixels here is going to be also 2. And then here we're going to say that our size t pixel right IDX, we'll call it, and pixel buff IDX. So everywhere we were using pixel IDX before, now becomes pixel right. Okay. Then when we switch this, we call I guess we call this display IDX. And this can just be bool. So we are going to write into S pixels at display index. Okay. Here we have S pixel right IDX is 0, and then S display IDX is equal to not S display IDX. Okay. We replace the surface with S display surfaces at display index. Okay. And so we should be double buffering now. We should be, right? Every time we write to the correct one. And then we can mem set this again. Sure, fuck it. I don't know. We don't have to get perfect. Pixel IDX. So this is pixel right IDX and S display IDX equals 0 or false. Oh, whatever. Who fucking cares? Who fucking cares? We initialize both pixels. We initialize both display surfaces. We initialize our console. Feels like it might work, to be honest. Feels like it might work. All right, let's run it. It also might not work, right? Let's not get crazy here, but for real, how the fuck does somebody know how to write a driver for the GPU? Where else all that knowledge lie? We did a lot of reading. We did a lot of reading. And we didn't really know a lot when we started. And you can see that we're just a lot of what we're doing is just like following crashes, to be honest. We follow a lot of crashes. And we just kind of slowly get somewhere. I guess here we can run this in GDB and just kind of see what happens. GDB args. I hope that we built QEMU with debug symbols. Otherwise, that's going to be really unfortunate. But yeah, I mean, you can watch the whole learning process. It's all on YouTube. Some of it might be a little bit paywalled. Some of our like background reading and stuff. But if you want to know, we just kind of start. You just go. You go like, I want to do this. Google, ChatGPT, Google. Only a little bit of ChatGPT. We don't want to get crazy. And then try stuff and see where it falls over. Our surface is not aligned. He is not aligned. That's annoying. That's annoying. Is it console GL line 50? Okay. Console GL 50. So he wants the surface bytes per pixel. And the stride needs to be aligned to that bytes per pixel. Okay. Right, this is, QEMU is aligned. The stride of the surface, so this is just gonna be like an equals, and percent %m equals 0. So he wants the stride over the bytes per pixel to be 0. And it's not? This is, we should check what this is. We should have, I guess we run in GDB again and just looked at values. Run. Run, baby. Run. All right. Root test app dev dri card 1 and backtrace. This is not in the assertion this time, huh? It feels like maybe more memory corruption. Run it again. Root dev dri card 1 test app. Okay, P. Like arithmetic exception. So can we check this? Fuck. Yeah, we're not even seeing like we're not even really seeing a assertion failure here. It's just like memory is fucked. Is kind of more what this is sounding like, which means that we very well could have done something fucking stupid. Right? I'm not against that at all. Not against it. So how could this be happening? Do we have our backtrace still? So we're kind of in replace surface. Okay. Which we're kind of just being like, yo, throw me this shit, man. Now, it could be that we actually need to reset the display surface here, right? It could be that this data is not just like a backing store for this thing. Like this might not be legal, right? We saw in the vert.io version of this thing that they were actually recreating this thing every time. So we can just do that for now. Fuck it, you know? I don't mind. I don't mind. So we'll do s display surfaces at s display index is equal to our shit show command create boom, right? So we create this thing from our s display index, and surely we have to free the old version. So what did they do there? Where the fuck they were? I don't know where I am anymore. I'm lost. GPU. So they actually aren't destroying the display surface, surprisingly. Surprisingly, I guess maybe it's owned by this and it will like automatically free itself. They do call free display surface on the old surface, so we actually don't have to think about it at all, which is kind of sick. So in reality, we don't even have to hold this thing. We can just kind of do this. And we don't need to do this at all. Kind of just do it here. Boom. Where the fuck we just were? I got lost again here. Maybe. Maybe. Oh, yeah, that explains a lot, too, because if they were freeing the old surface every time, we were just using invalid memory. Yeah, that makes a lot of sense. Makes a lot of sense. Come on, baby. Let's fucking see it. Let's fucking see it. R. Serial. Moment of truth. Moment of truth. I don't know why I'm acting like I think this is going to be the one, but I really do feel like this is going to be the one. Fuck! Fuck! It felt so close. I mean, we're not crashing anymore, but for some reason we're just seeing like nothing here, which is pretty unexpected. Pretty unexpected. Pretty unexpected. Do they do anything else in theirs? They call update scan out. But I don't really think this is doing anything interesting. I guess we don't really know that the pixel format is right. Right, we could try reversing the pixels again. Just to see. Just to see. You never know. Because it could be that the gray was just from everything being alpha 0. You know? It's a very real possibility. Okay, let's we don't need to run this GDB anymore. We do not need to run in GDB anymore. We can run it raw. All right. Test app, dev, DRI card 1. Still just gray. Still just gray. So what's weird to me is we had this working like at some point, right? Right? Maybe we didn't. I thought we did. I thought we had it showing, but I could be misremembering. Maybe I am. Can we just do something like how do I want to do this? Can we just try to show like white or something? Like on realize? Right, can we do like a mem set pixels like 0xff for pixels len times 4 or something? I just want to see something. You know? You know? I guess we kind of expect it to look white now. So that's working, right? We do have like some way to draw something. Now, maybe it's related to the fact that we're doing this so frequently, right? It could be. Could be. So here we create the display surface from this thing. Then we don't we memset the other one, so it should be kind of fine. And maybe we'll try only doing this once. Set once. Return. Right? We only do this one fucking time. So we can do like set once here. And then down here. right? We can do something like this. So here he's saying not initialized yet, which is good. That's what we expect. Then we try to run this. We segfault. Surprise? For sure. It's definitely a surprise. Like, that's from here. We do initialize these, right? Yeah, we malloc these. Pixels, pixel right IDX. Set once, display IDX. All of those are set. Then here, I guess maybe the length of this 1024 times 4. I guess here we want pixels len times 4, just to be sure, but I don't really see why that would matter. Oh no, this is stride? Line size. I guess we didn't really look up what line size here means. Could be in bytes, could be in pixels. It's really unclear. They use line size here. But we can look here for a clue. Host mem over height. Pixman image create bits. What is his thing? Is it in bytes or is it in pixels? Row stride bytes. Row stride bytes. Okay. So 1024 times 4 does seem reasonable. Does seem reasonable. Then I'm not really not seeing what we've done wrong here, to be honest. Unless it like frees the underlying memory as well when we call free on this thing. That'd be fucking frustrating, but it's possible. Although this should only happen one time, so I don't really think that should be the case. I guess fuck it, we run in GDB again, right? Guess that's kind of the only answer here. Run, run, run. Let's give him a sec. Test app, dev, DRI, card 1. And yeah, he is segfaulting again. Memory region in Sphero right, in Sphero do DMA. Oh. Can we do S? Oh, I'm an idiot. I'm an idiot. We need to reset the write index when we, or else it will write to an invalid piece of memory. That is true. It is true. So we're just gonna do this here. This stuff we need to always reset. Yeah, I think that's fine. Everything else is probably okay. Make ninja, ninja, ninja. All right, all right, all right. This is the one, guys. This is one. So what are we hoping to see? We're hoping to see one frame of yellow smiley face. Dude, there's something in my nose. That's the fucking worst. Like right up at the fucking top. Something crawled up there, like a little bug's up there running around. Not actually, but that's how it feels in my brain. I'm like freaking out. But it's fine. Okay, so what do we see here? We do just see gray. It being gray is so surprising to me. I guess that's what happened when you have alpha 0. Oh my god. Oh. Okay, it's fine, it's fine. Yeah, I mean, my gut says that it's using zeroed out memory in some way. But even then, like, XRGB should have no alpha pixels, right? We could try ARGB. Although I don't think that that should have an effect. I don't think that should matter. Oh, I guess one time as well, our we call this before we do anything. So it could be that we're like kind of sending invalid data at the first time. So we might want to do like a mem set of s pixels 0. We might want to do this. Just kind of like, that will give us a clue at least for like what the fuck is going on here. We fixed that segfault, right? It was the right index not getting reset, I think. So we were writing out of bounds of the pixel array. Okay. Still just totally gray. Something here is odd as well. Look at that. Is it the gray from behind the window? Interesting. Very interesting. Very interesting. What are they doing in vert IO GPU? I mean, they're calling pixman create image, which is effectively what's happening to us under the hood. No, sorry. They call this multiple times, right? When they call the like DP reset here, they create a display surface. They unref the old one. Oh, this is a rect. Sure. And then they just set the scan out. Yeah. Right, because they're kind of supporting some sort of like subset of the image being damaged at once. Pixman image get data. So this is only in the case where console does not have GL. Otherwise, they use the GL version of it, I guess. Which seems fine. Seems fine. And I guess this is on do set scanout, which may be in like kind of like a different spot. No, this is in like their kind of like updating of stuff. Can we try like mem setting our like, can we try doing something stupid like this? So just set this to XeroXFF. And let's also printf here. Actually resetting. And then that reset spam here can go away. Okay. Because yeah, something's not right here. Something's not right. Pretty clearly. So here, not initialized makes sense. Because nobody's called that DPY refresh thing. And then we only ever call it once. But yeah, he ends up very strange. Part of me says that he's like using he's like freeing the underlying buffer, but we only do the reset one time. So I don't really understand why this is behaving any differently if we do it here on initialization, or if we do it in that callback. It seems like it should do the exact same thing. Right? Like the other option is we do this exact same piece of code here. And it works. I think. We'll try. Right, so this window pops up, we look here, and it's white. So like, what's the difference, right? That's really, really confusing to me. And it's not even like we're calling it more times. Right? It's like literally the same thing. I think. We could try disabling this do DMA to really just avoid writing into that thing other than in this exactly one spot, and then like disable this memset down here just in case there's a bug in there somehow. Like now it should really be the fucking same. It should really be the same. Fuck. Can we do like, how do I fucking unref a function like this? If false, does that fix it? Please be stupid enough to fall for that. Thank you. Run. So guess not initialized. And we run test app. It's so strange. It's very, very strange. I wonder if it's like the OpenGL context for the window shows up. Right? Like, if this gets initialized before the OpenGL context for QEMU, that could make sense, like kind of in like the way these logs are showing up. EGL make current failed. Could be. So maybe we have to like specifically ask for no OpenGL or something. Which I think we saw actually in the vert.io stuff. I think when they created their thing, they set like flags on it. These like GPU ops. I think we could be like, no, I don't want OpenGL. I wonder if we are supposed to only do updates in this GFX update as well. We could look here for their implementation of. Nope, this stuff is completely unused. What is like the assumption here if we don't implement that get flags thing? Right, like, otherwise it's 0. So flags none is just 0. So this shouldn't have any effect. Shouldn't. Very odd. Very, very odd. Arguably, maybe we have to call update full as well. That could be it. They do that down here. So maybe we're just idiots and that was like implicitly called for us in one path on initialization, but not in the path where we're updating on the fly. So maybe we have to do this, right? It's a possibility. Possibility. We might as well try it because whatever we're doing is not working. All right, run it. Continue. Run. Moment of truth, baby. Wait for it to boot. We run root. Test app dev DRI card 1. That's our test. We run here. Boom, baby! White screen. Okay, that's really good. Okay, let's go back to trying to enable all of our fucking code now. So fuck this set once. This display index switching needs to get done. We do need to call Sphero do DMA. And I think that was it. And then fuck GDB here. Because I don't want to wait for it to boot. We run our thing. And we go into Sphero. It's not initialized, but if we go to here, we run root test app dev DRI card 1. He's just constantly white, which kind of makes me think that Sphero do DMA is not happening. Well, that's confusing. Oh. A few things all happening at once here. Okay. Just a few pieces of code, multiple pieces of code in the wrong spot, causing bad behavior. But this is the one, guys. This is the one. There's no way it won't be the one. Wait for our machine to boot. One day I should speed this up. But for now, we live in a world where I have not. Oh, let's fucking go, baby. Dude, let's fucking go. That's so sick. Look, our GPU works. Guys, our GPU. Look, our GPU. It works. It works. That's actually so fucking cool. Do you guys think KMS Cube works? I wonder. No fucking way. No fucking way, dude. I mean, it's slow as shit because we are being slow as shit. But let's fucking go. Let's fucking go. That's a fucking GPU, baby. Oh, that's so sick, dude. Can you tell I'm a little stoked? Can you tell I'm a little happy? So what have we done here? We wrote application that raw dogs Linux graphics. He allocates a buffer to write some pixels into. He writes some pixels into those things and attaches them to a frame buffer. The frame buffer gets attached to a plane. The plane gets attached to a monitor controller. The monitor controller gets connected to a connector. All of that goes through like the typical KMS kernel mode setting subsystem of the kernel API of the kernel. We implemented a driver that hooks himself up to that API in some way, hopefully correctly enough that he can display some stuff. We implemented a PCI device that does DMA transfers from host memory or from like guest memory. So like when we allocate these buffers in our virtual machine, they go into like, they scatter across the land. We collect these scattered pieces of memory and feed them to the GPU one by one and say, please render this. We have like the dumbest fucking PCI. The dumbest PCI interface ever is just like write the address and the length to this thing and it blocks the write until that's done. So that's why this is running so fucking slow. But it's fucking doing something. It's fucking doing something. That's pretty fucking sick. Pretty sick. Okay. I'm really happy with that. I guess that means there's nothing more to do today. Thank you for watching, guys. If you like what you saw, we stream most days 12:30 to 2 or 12:30 to 4 o'clock Pacific time. It is 4:10 Pacific time now, so 3.5 hours ago to now is the typical amount of time that we are running for. If you are new here, there's a YouTube link in the Twitch description. We have all of our projects organized into playlists. We're working on demystifying the Linux graphics stack now, but there's a lot of other cool stuff in here if you want to go check that out. There's also Happy Hour playlist, which is the 12:30 to 2 segment, where we kind of do like, you might see some like reading in here to try to like ramp up on topics. You might see some like kind of like side projects that aren't really like important, or some like bug fixes, code cleanup, unit testing type shit will be in here. But that is paywalled on the member section in YouTube as well as on Patreon. They got uploaded to both. If you're watching on YouTube, there's a Twitch link in the YouTube description. Swing by, say hi if you feel like it. There's a GitHub link in the Twitch description. This stuff will end up under the GPU testing env. It looks like since we have a feature, it is worth cleaning up and pushing soon, so it should go in here in the near future. I think that's it. Like, subscribe, Twitch Prime. And I guess we'll be back to the plan for like how to progress this project now is I think the next thing I want to do is fix up like create a fixed shader pipeline that will just render like the Suzanne monkey, right? That demo, our little demo app of let's see if we can find it. I think it's in our Swayland client. Zig out bin Swayland client. The next task is going to be to try to port this onto our GPU, right? So this is using OpenGL right now and a few like model transforms, as well as like, you upload your object and stuff. I'm kind of hoping that if we make like a really, really fixed shader pipeline, we might be able to do this in our GPU, but like without all of the OpenGL stuff. So that's probably where we'll go next. That's probably tomorrow. If I'm so fucking lost when I sit down at the computer tomorrow that I don't know where to start, then it won't be, but it probably will be. So tune back in tomorrow if you want to see that. Otherwise, I will catch you guys whenever I catch you guys. Thank you for watching. YouTube, goodbye, and Twitch, let's find someone to raid.